All right, good afternoon, everyone. I hope you have enjoyed the poster session and had a good lunch. Now it is my pleasure to welcome and introduce our next keynote speaker, Professor Jessy Grizzle from the University of Michigan. So he is the Elmer G. Arbor Distinguished University Professor and the Jerry Carroll Levin Professor of Engineering at the University of Michigan. He jointly holds 16 patents dealing with emissions reduction in passenger vehicles through improved control system design. He's a fellow of the IEEE and IFAC. He received the Paper of the Year award from the IEEE Vehicular Technology Society in 1993, the George S. Exalby Award in 2002, the Control Systems Technology Award in 2013, the Bold Lecture Prize in 2012, and IEEE Transactions on Control System Technology Outstanding Paper Award in 2014. His work on bipedal locomotion has been the object of numerous plenary lectures and has been featured in many magazines and television programs. Let us welcome Professor Grizzle.
Thank you, thank you. Is the mic working just fine? Everybody's okay. So I just want to give a strong appreciation for all of the fabulous organizational stuff I've had. It's been great working with Ravi, Sarah, Khaled. It's been really, really nice. You guys make everybody feel special. Now I want to thank my team. Two of the members that have graduated and got on to great things are here, Ali and Haywan, so Ali Reza. So one of the great things about being in a fabulous Big Ten school, whether it's Illinois or Michigan, we're always arguing back and forth, is the quality of the students that show up. And it's seen here in the group in CSL for sure. But I also want to thank Jonathan Hurst, who's been a very close collaborator of mine. I started working with him when he was a PhD student at Carnegie Mellon. He's been designing robots. Okay, so just a few quick comments on why do we care about robots. I mean, normally you don't have to say anything. We just do robots because everybody loves robots. But in terms of bipeds, I get a question a lot is why don't we just use a quadrupedal robot to go into a factory or something, into a house? Why send bipeds? Quadrupeds don't fall down near as much as a biped. Well, the problem is our homes and factories are built for upright, narrow machines, organic or not. And so either we can redesign all the factories such that something like Big Dog could go up the stairs and do it, or we have to make our robots stable enough that they can operate in that environment. When Fukushima happened, it was an American robot that showed up 1 week after the disaster, and it took them one additional week to train the robot to go upstairs. So that's not acceptable. We want them in our homes, and of course we wouldn't want tracked robots going in many places in our homes. If you've had the misfortune of an accident, you don't want to replace that with a wheel, so you're going to have a lower limb prosthetic, and they are now just as advanced as any leg on any robot. And then finally, I mean, I've proven lots of theorems in my life. I see lots of people in this room who've had that pleasure as well. And nobody comes knocking on your door and says, I want a tour of your latest proof, okay? What they want is a tour of the robot lab, and it's really a lot of fun. So that's why we do it. Okay, so I had this funny title, Science Fiction to Science Fact. So let's just look at the state of the art. What do I deal with when people come to my lab? What are their expectations? It's based on TV, right? And these science fiction robots are better than people. Better than anything you can imagine yet getting a machine to do. So what's the reality? So this is a DARPA Robotics Challenge. Why are you guys laughing? That robot won $1 million. Nobody here wants a check for $1 million? It's the only robot that had no wheels on it at all, or tracks, that actually won money. Okay, so it's the only true biped. But you can see it's very still clumsy. I mean, literally, in Jerry Pratt's group, humans were deciding where the robots put its feet when going over these obstacles, okay? So the robot's not doing any of the planning. It's like the Wizard of Oz. You pull back the curtain, and that's what's going on. And how's that going to work out for you, big boy? Not so well. So obviously he did much better on Sunday, and that's when the robot won $1 million, came in second place. Very impressive. Excuse me?
Was it on the same base ground?
Yeah. He did they practiced on Friday with nobody watching, and then they did the competition twice, and you got to take your highest score. That's how it worked. That was the scoring rules. And so they learned a lot on Saturday, apparently, and Sunday did much, much better. So these are robots I've been working on. They're not nearly as sophisticated as that humanoid, but in some sense they're much, much better for doing science. I mean, I started just drawing down very simple models, doing nothing but theory until this French robot Rabbit was built. And then we went on and got robots in our own lab. But what I've always been focusing on is trying to get dynamic locomotion, things that move fast and respond well to disturbances. So here's Rabbit. I mean, this is really old stuff now. This is like 2003. But it's carrying a weight that's not modeled, handling disturbances in a reasonable way. Rabbit was a gold mine for proving theorems and developing fundamental notions of locomotion. It's because it was simple enough that you could start making progress. If I had started with something like I'm working on now, quite frankly, I would have just given up. It's just too hard. So this is Mabel. The idea was to build a machine that's much more capable than Rabbit, but yet still something that we could then build on from the theory we had with Rabbit. Like Rabbit, it's attached to a boom. And I always get this question, is the boom holding up the robot?
Come on, Gary, you're supposed to fall.
Anyone hates this section? Because 3 days later, the robot's on an operating table, and he's got an electric saw in his hand, and he's cutting the robot in two. Turned it into an industrial wasteland for a while. So the boom doesn't hold up the robot, but it's designed to be highly dynamic. So there's Jonathan Hurst, the builder of the robot, exercising the springs. It can act like a pogo stick. And so with that, this is what Kaushal did. The top speed it reaches is 3 meters per second, so it's equivalent to a 9-minute mile. So many of you can outrun it, but the robots keep on coming, man. That was our first video to go viral. People like Robot Blood and Gore. But we're always trying to challenge the machine with uncertainty in the environment. That's what we want. We want theory that others can use. It should be transferable to broad classes of robots, and I'll talk about that more at the end if I don't spend too much time having fun on the stuff before that. But we want theory that works in the lab with, of course, we don't have models of all of this, right? So it has to be robust. Now, when you see this, the big thing everybody was telling me for years, and something I understood too, is that eventually it's got to go, right? It's because if you want to get robots outside, they can't have booms, and so Mabel was retired. She was on display at the Field Museum in Chicago for about 6 months, and now she's on tour, and I don't even know where she is in the U.S. now. But definitely robots outdoors. And so Jonathan had completed his degree at Carnegie Mellon after building Mabel. That got him a job at Oregon State, and then he, as PI, led a couple of us on a DARPA grant to get money to build a 3D robot. And so where Mabel's legs could not move inwards and out, so there's no sideways motion. So if you're falling sideways, you've got to step sideways. That's what the boom handled. This robot can move its legs sideways and do its own stabilization. So the first student to work on this robot was Ali Reza here. And so, yes, I'll show you more later, but it's quite capable of stabilizing itself. And it's got a pretty natural motion. But you can see, we're terrified it'll fall and break itself. We've got cables on the roof there. Quite normal. Okay, so what I want to do now is go through some of the model-based feedback design we're doing. Any undergraduates here? Few? Are you feedback specialists? Oh, maybe I don't need this next stuff then. What's a feedback loop? Here's my take on it. So here's our system. We need some means of having the parts move. So we have motors attached to links and something to measure what the robot is doing. So we're using encoders, and there's also an IMU to get the orientation of the body. Okay? No cameras or anything like that. So that's our system. What we want to now do is come up with an algorithm that takes these things as inputs, using the measured quantities, forms a sense of balance for the robot. So that's what we want to have, is stability. This kind of grace that you saw in the running, the ability to handle terrain variations, etc. That's what we want. So that's our feedback loop. And then it should also take the reference commands. We should be able to tell the robot the kind of actions we want. Should it be walking over the terrain? Should it be running over the terrain? Maybe we want to give it some feed-forward information, like there is a big slope up ahead, even though if you don't have a camera, we'll just tell you, whisper it in your ear, okay? So that's what we're doing. And it's just like in your homework problems in your courses, you want to do model-based design. So here's Rabbit, and that's the inertia matrix for Rabbit. No problem, right? Well, the amazing thing is you can do strong analytical analysis of models of this complexity today, so that's what we're doing. The other part of the models, besides just the huge size that you wouldn't typically do in a homework problem, is that they have multiple phase, and they're called hybrid. They have switching aspects in it. So in single support is when you get these Lagrangian dynamics that I was just playfully having fun with you with. But then when the swing leg comes forward, it decelerates very, very rapidly. It takes about 20 milliseconds. And so we model that as being instantaneous. And the reason we do that is if we put in a compliant model of the ground deforming, we'll actually introduce more parameters trying to get the spring constants and the damping in that we surely don't know, and surely changes when we're walking on this carpet versus walking on the sidewalk outside, that what looks like making the model more complete and more certain is actually introducing garbage into the model. So we're better off with this simplification of an instantaneous impact, and this gives us a hybrid system with continuous dynamics, switching, a new initial condition, relaunch the dynamics. Okay, so that's the models. They're hybrid and they're fairly big dimensional. Let's talk about another piece of at least the robots I work on. Rabbit had no feet. Mabel, 99% of the time, had no feet. And we put really simple feet on this one, but they're unpowered. So why do I do that? So that's how robots were walking when I started in this field. Okay? Really slow on big feet. This is not good walking. That's shaft. Anybody recognize where that robot placed? It won the trials that was before the DARPA robotics challenge this past summer. So that was the first place robot for doing the preliminaries for the trials. That's how it walked. I mean, it's fantastic flat-footed walking, but it's just walking just the same as that robot was doing 20 years before that, okay? And so there's all kinds of theory. 95% of it works when the robot can maintain flat contact with the ground, because then if you have big, powerful ankles, et cetera, you can orient the shin, and with the knees, you orient the thighs, et cetera. And the problem comes when you break that assumption, and it's really easy in 3D when the feet are narrow to roll side by side, okay? So what I oblige my students to do, and me as well, but mostly the pain falls on them, is that we work with robots with little tiny feet with the idea that if you can keep this robot upright and elegant, then you put any kind of foot on it you want, and it'll be just fine. And so this is just a quick film of Atlas trying to stay fully actuated. It's not easy, okay? And that's Jerry Pratt, and he knows as much about humanoids as anybody in the world. A little bit of math, and then we'll get away from the math again, and we'll come back to the math in the middle and then go back, okay? So if you have one of these hybrid models, how do you find a periodic solution and check whether it is stable? In the sense you perturb it, you converge back to it. Okay? So what we do is use the method of Poincaré. It's old, just like Fourier. So this is a set of points on the ground, in the state space where the robot's front foot is flat on the ground. Okay, so you take a point in that, follow it around with the impact map, so go boom. Now apply the Lagrangian dynamics to it. Whoops, went the wrong way. Okay, you will come back, not necessarily to where you started, but this gives you a map from this hypersurface to the next point, and that's called the Poincaré map. Now, if this point lines up with this point, guess what you have? You have a periodic motion, okay? You found it. So equilibrium points of this discrete time system, they're called fixed points of the Poincaré map, are periodic orbits in the full hybrid model. Okay, so that's how you find those. And then just the same way you check stability of a discrete time or exponential stability of a discrete time map, you look at its Jacobian, you check the eigenvalues are inside the unit circle, then you have local exponential stability. So you'll have a tube about this trajectory guaranteed, and you do it by proving there's an attractive region on this reduced set. So that's the beauty of the Poincaré map. And we'll come back to that in a little bit. Okay, everybody with me so far? Am I speaking too fast, or we're good? Okay, so we'll give you the idea behind what we do. We'll have a little fun with it, and then we'll come back to some experiments. So I do something called virtual constraints. The way I like to explain it is to use notions from kinetic sculpture. So this is Theo Janssen. He doesn't know who I am, and I know who he is. That tells you the relationship of force here, okay? But he came to the Michigan campus and gave a really nice talk, and that's where I discovered what he does. He builds these really complicated mechanisms, okay? And this is how they work. So there's a central crank going down the mechanism.
To make things that look so close to being
This is one of the beaches of Holland where he's turned these things loose. He calls them strang beasts. So go on YouTube and look them up. They're thrilling, okay? So there's a crank, and then even though he's got dozens and dozens of legs and hundreds of links, everything is synchronized by this one variable moving, okay? So fundamentally, it's 1 degree of freedom. How is that happening? It's because he has all these physical constraints that are doing the synchronization for him. Okay? So what we do is take this idea and use it as a programming method. And let me tell you what that means. So you could use basic high school trigonometry and write down all of the angles of the various knees and hips and whatever you want to call those joints as a function of the crank angle. And so Theo Janssen's choice of the lengths of these various bars gives you sine, cosine, inverse, arctangent, whatever here, okay? Now suppose you disconnect the things from the central crank, and you add motors and a way of sensing where things are, and then you give yourself a feedback problem, drive the error from what the physical constraints would be doing as these functions to 0 asymptotically, then you will have imposed this relationship with feedback control. So physical constraint, this is virtual because it's MATLAB code. Theo Janssen, to change his gates, he has to go to Hacksaw and reglue all these things together. And for us, we just change lines of code in MATLAB, okay? It's that simple. So that's what we do. There's a crank. Where's my crank? So if you look at the line connecting the hip to the stance toe, it's a hybrid clock. Okay? So it's monotonically increasing as long as the robot's walking forward, and then it resets each gait. So this one goes round and round, so it's got continuous, or on this circle, but we're just going part way and resetting, and that's what we have. So we use this as our crank angle. And so then what we're doing is we program up a gait by programming the knee angles and the hip angles as a function of this virtual crank angle. And I'll have to tell you a little bit about how we choose those functions, because that tells you everything about the gait. And so here's us. So Ollie and Brian and I are at Oregon State. We've been working with the robot for 2 days. We now figure out which all the motor controls, all the sensing, all of Jonathan's coordinates, all of our coordinates, and we've got the virtual constraints implemented. And all the students are doing is moving this angle forwards and backwards, and you can't tell if there's a whole bunch of gears and funny things in there moving the leg or whether it's a computer program, right? It's the same thing as far as you can tell with this playing out. So is it MATLAB code, or is there really gears inside the robot making that happen? So that's the notion of virtual constraints. Okay, so this is how we write them. Things you are controlling, knees, hips, etc., their desired evolution. And then you have this gait timing variable, or the virtual crank variable, and you use feedback to drive them. And there you can do inverse dynamics, you can do control the up and off functions, you can do MPC. I don't care how you impose those constraints. All I want is that this is asymptotically assured. Now, often I talk a lot about the geometry and et cetera. Today I'm just going to do a few little pictures, but constraints give you invariant surfaces. So these constraints translate into relationships on the state variables of the robot. And so it's moving on a much lower dimensional surface, which Burns and Isidori studied in their fundamental work in the late 80s and early 90s and called the zero dynamics. And what we've done is take that into the hybrid arena that shows up in robots, and we make these surfaces also invariant under the reset map, and then we have these hybrid zero dynamics. And that's kind of my thing, hybrid zero dynamics. But why I love them is, you see, like on my robot Marlowe, there's 6 actuators. So I have 6 of these and their velocities. There's 12 states that I know exactly what's going on almost. I mean, the actuators are tied directly to them. So all the uncertainty in the model, I can use my actuator power there very effectively. And then I have anywhere from 4 to 8 states, depending upon my springs and a few other things, okay. But I've at least divided the model dimension by half, but usually I'm removing at least 2/3 of the model. And it's the choice of virtual constraints shapes this surface over here, and that's what gives me the inherent stability of my action, is designing this surface correctly. Okay? So if I design this surface correctly, and then I use any method I want from feedback control to drive myself to that surface, that's the inherent method that I'm implementing. So it's a divide and conquer, and they look separate, but it's the choice of virtual constraints that makes this the right thing to render attractive and invariant in the closed loop system. Okay, so let me tell you a little bit of how we design those. So once again, I said it before, this is my error term. I want to make this small. These are the things I'm controlling, knee angles, hip angles, but maybe something more elaborate. Then I've got this function, and what I've done here now is introduced a set of parameters. So these are splines, and I'm going to choose the splines to set the shape of this surface, how the swing leg rises from the ground, etc. Okay? So I'm going to set up a problem, a design problem, of now I'm really designing the virtual constraints. And so what we can do is use some good old nonlinear control theory, and we can determine, we can determine the torque it takes to move along one of these surfaces. And so what we do is minimize energy required to move on the surface, divided by distance traveled. Okay, so this is cost per energy, and if you normalize by gravity, this is some nice dimensionless quantity. We set up a little optimization problem, and then this is where everything matters. It's all in these little constraints here. Okay, so the constraints, my actuators only have this much power. I have a friction cone depending upon what I'm walking on that maybe is 0.6 if I'm lucky, but if it's on a slightly icy day outside, it's maybe 0.3 or 0.2. I don't want to be stomping on the ground and breaking things, so I want to limit the velocity of my feet at impact, etc. Okay. I want to walk at a given speed. Maybe I want a periodic behavior, or maybe I want to transition from walking, as you saw Mabel, into running. Okay, so all of that's in there. If I know the ground is mostly flat, my swing foot clearance will be really, really low. You guys do this all the time. So outside my office, it's nice linoleum and flat. And every once in a while, that linoleum kicks up a millimeter. And I can just watch people trip on it all day long, okay? That's how efficiently we walk indoors. And if you use that gait walking on the sidewalks at Michigan or in Urbana, you'll just die, right? So you adapt your gait to what you expect the environment to give you. And so when we go outside, I tell the robot, you need a minimum of 5 centimeters clearance here. Just don't even think about it, okay? Don't drag your feet across the floor, etc. So these is where all the engineering judgment, and then the optimization finds magically how the knees and hips and everything should evolve so that these can do, or it says there's no solution, right? And it'll say, sorry, with only 3 Newton meters of motor torque, 3 Newton meters of motor torque, you cannot go at 1.4 meters per second walking, okay? It's just not going to happen. Give me more power. Okay, so that's how we get the beautiful constraints that you saw. And now let's talk about stability. So this is where choosing what to control is kind of important. So let's look at the planar case. So this is rabbit. I could control the angles of the knees and the hips like I've been talking about. Why not? I could have a more world frame point of view, the height of the swing foot and maybe its path. The angle of the torso with respect to the world frame. Heights of the hips with respect to the world frame. These are all body coordinates. These are all world frame coordinates. Very different, right? So you'd expect that one choice versus another should give you different stability results. This was a surprise when we discovered this. If you have a robot like Rabbit or Mabel with stiff springs, you have 1 degree of underactuation. Stability is independent of the choice of outputs. Okay? Completely independent. It's the orbit is the only thing that matters with this method of control. Okay? Completely doesn't matter. What's important, though, is that stability is kind of a minor thing. You might want bigger or smaller basins of attraction and how you respond to disturbances. So even this result is true in the sense of stability, but it's not true in the sense of, hey, all outputs give you the same basin of attraction and how much torque it takes to recover from a perturbation to the periodic orbit. And what's really sad and drove us nuts for a long time is that as soon as you remove this 1 degree of underactuation and you go to robots like Marlowe, where you're balancing in 3D essentially on a foot, and so you can pitch, roll, and yaw, that's 3 degrees of underactuation. Oh boy, does stability matter, okay? And that drove Ali crazy as the first PhD student working on this. So let's see how that works out. So here's a 3D robot, and the obvious thing to control on it are the knee angles, the angles of the legs with respect to the body, and then since in 3D you have these extra coordinates which moving the legs and the frontal plane. So those are the actuated coordinates. And that would be really how we thought about rabbit here, or Marlowe for that, Mabel for that matter, and then adding some ideas of doing things in 3D. You do our beautiful virtual constraint design. You calculate the eigenvalues of your Poincaré map. That's bigger than 1 in magnitude, okay? Outside the unit circle, robot falls. Okay? So, this is what made me really proud for a short period of time. Working with Christine, et cetera, I kind of figured out, hey, I get it. When you're falling over, the leg needs to come out, keep the center of mass between the 2 feet, so I'm going to control the horizontal displacement in the frontal plane as a function of the angle of the center of mass, okay? So in this particular model we were looking at, hey, I'm a genius. I use physics. Eigenvalues are now inside the unit circle. And I was like, yes. And then we do the same thing on the robot in our lab. And Ali comes and shows me that this is the very best, we can do is 1.2. And he basically has a proof. And I'm going like, wow. So we did some really nice event-based control and got Marlowe going. And then after Ali graduated with a postdoc in Bryan, we kind of took on this problem of systematic selection of outputs. And that's what I'd like to tell you a little bit about. So how can you choose these virtual constraints in order to guarantee stability without messing up the beautiful periodic orbit that you have designed? Okay? So here's the idea. I'm going to show you that you can introduce families of controllers, and they don't change the basic periodic orbit that you've already designed. Okay? And then I'm going to show you a formal stabilization problem of choosing these parameters to make this orbit exponentially stable, if there is a choice, okay? If there is a choice. And then we'd be systematic. So here's the idea. So we design these orbits by zeroing out these virtual constraints. So forget about this matrix for a second. I design my orbit. I take all of my configuration variables and I evaluate them on the orbit as a function of this virtual crank variable. So then, on the periodic orbit, this is already identically 0. It doesn't matter what I put here. All I've got to put here is enough restrictions such that my decoupling matrix is full rank and blah, 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 some things that are basically generic. Okay. Then now I can change all of these linear combinations of variables in ways that my brain can't process, but optimization programs are perfectly happy to help us do. Okay, so that's what we do. No matter what I have here, I give the same periodic orbit, but I won't have the same stability, as I'll show you in a second. But if you like LQR thinking or whatever, this would be closer to the family of controllers that like Russ Tedrick uses, for example. But you can do the same thing with his stuff. Okay, so here's the setting. We've got this crazy hybrid system. We've introduced a family of controllers. We did the orbit design based upon all the limitations that this robot has in terms of physics and what we're trying to get it to accomplish. With the existing set of constraints we did the design on, we might not have stability, and now we're trying to enhance stability. Okay, so here's the picture of what I just said. So this should be a like hybrid, but imagine that we're just doing a periodic orbit and forget about the hybrid thing, okay? This is one of the zero dynamic surfaces, right? As I change my parameters, I'm changing this surface. As I change the parameters, that surface changing changes the directions of the vector fields pointing to it, is the idea. Okay, so if it's really just two-dimensional, then maybe I could just do this by hand and try to make sure that all of them point in and then I have stability versus going like that. It's instability, right? But, you know, these high-dimensional models, good luck. So what we do is we use this Poincaré map that I told you about. So because the orbit doesn't depend upon these parameters, this fixed point doesn't vary with my controller parameters, which are changing the virtual constraints. What we want is a value here so that this matrix is Hurwitz. Its eigenvalues are inside the unit circle. Okay? So let's do a little Taylor series expansion of the Jacobian with respect to the control parameters, and you'll get something like this. When you're not changing anything, this is your nominal Jacobian, and then now these are the next perturbation terms in terms of the deltas that I'm adding to my control parameters. Objective, choose those deltas such that the sum of those matrices is Hurwitz. Okay, so when I was a grad student, we talked about doing static output feedback control and how that was an impossible problem to measure and always do dynamic and stuff like that. This is actually equivalent to static output feedback, so it should be impossible. But it's not anymore because of computational tools, and this is why. Okay, so to be Hurwitz, I can look at eigenvalues, but the other thing I can do is build a Lyapunov function. Okay, so introduce a Lyapunov function, and I want its increment to be negative. If these parameters are constant, checking this condition is a linear matrix inequality. If I freeze a guess for the Lyapunov function and change this because it's linear, that's another linear matrix inequality. And when you write everything down, it's now bilinear. So it's a bilinear matrix inequality. It's not convex, so you don't get global solutions, etc. But it's kind of a, I don't want to say friendly perturbation, but it's at least true. And how a lot of the solvers essentially work is freeze this, iterate on this, freeze this, iterate on that, and then you can prove that you converge to at least local minima and stuff like that. And the solvers are getting to be pretty darn good. So that's what we do. And we did it on this original model where I could use my physics, and then we did it on the robot I really care about, where my physics intuition for me didn't work. And what it does is it gives us virtual constraints which depend upon the crank angle I always knew and loved, but it also told us how to introduce the roll angle properly into the designs. And this is what we get. So you've probably seen this if you love Michigan football, because this is from the Big Ten network. So it's all dark because they're trying to make these really nice things. That's the producer. Oh my God, it moves. And so now Marlowe is stable without making just a lucky guess of what things are. And there's with the lights turned on, this robot still works. It's walking on stilts. 3 degrees of under actuation. Etc. More recent look. With Omar and Dennis. We don't use a camera, so the robot doesn't care if the lights are on or off. But it's more fun for us. This is in December. You see we've had a mild winter just like you guys. We've got a little gain controller hooked up to the robot. We're being very cautious, lifting the feet high, etc. This is another set using non-holonomic virtual constraints and testing them on the planar version of the robot. This is great uncertainty. And when we can do that without the boon, then I'll find a different problem to work on, okay? Hey, Juan, Ali, it's all yours once we can do that, okay? We can do a little bit. And this robot has a broken harmonic drive when it's walking. It's kind of amazing. It's even standing up. So that's some of the new stuff we'll be telling you about. And our goal is to be able to go over something like this. If you've been to Michigan and you've seen the wave field, it's pretty. Just blindfold yourself and give yourself a shot at it, okay? That's what the robot will be, blindfolded. And as soon as the campus police will let us, we'll be walking around and doing all sorts of stuff on the main campus diag. Okay, so I've got about 6 more minutes here, so I'll be finishing up well on time. We can have a little bit of a break and stuff. But what I want to close with is, why do we do all this mathematics for these machines? Because the people who just get their machine and then they use all of the intuition and hacking to make that one machine work, they always beat me to getting something done, okay? But the problem is they don't leave a recipe that I can follow or someone else can follow, okay? So my group is slow, partly because I always keep it small and I like to interact a lot with people. But we're after general principles. And what's really gratifying is that when you get the right papers out and the right books out is when other people pick up the work. And what they do is they send you a video of your stuff in action, and there was no phone call saying, what was the special sauce? What did you really mean here in this equation? You get it? Okay, that they can just use it, okay? So that's what we're really after, and I'll show you that that's starting to happen. And then the other thing, these humanoids, I mean, they're clearly operating far below what those machines are capable of, whereas I think we had Mabel at almost the limit of what it could do, okay? We optimized the heck out of that, and we will have Marlowe operating there as well. Because we're using analysis and things in the right way, we can actually find the maximum gaits that those machines are capable of doing. And so what we always try to do in our work is write up stuff in an abstract way. And it's really written up for hybrid systems, and you sort of abstract out the fact that it's a particular robot, for sure. That's the big thing, you know. This is just one of the simple early theorems and stuff, talking about energy loss and energy gain over the orbit and how those things interact for stability. And it was developed for Rabbit, okay? But it basically worked for Mabel. And, of course, this is another biped, so maybe that one should still expect to work. But I never thought about that, okay? That's much more complicated. It's got a human attached to it, okay? But Bobby Gregg looked at it and said, hey, that should work. So let me show you what these guys have done. And I won't show you what Jim Schmiedler's been doing at Notre Dame, but that's really nice. You should have Jim come and talk to you about what he's been doing. So this is work Bobby did at the Chicago Rehabilitation Institute, so just up the road from you guys. And I didn't talk about some of the other competing techniques, but this one literally involves, you deciding where to put the leg. And sorry, if I'm wearing this prosthesis, I will decide where to put the leg. The prosthesis isn't going to decide, so that doesn't work. And this requires you to walk flat-footed. And if I'm walking flat-footed, even with my jeans on, then I don't look like everybody else, and I am definitely not happy with this prosthesis, right? Because what you want to do is blend in with the crowd. As much as we want to be individualists, we don't want to be special in uncommon ways, right? So ZMP, no way. So this is what Bobby got. It's his brilliance, but it's virtual constraints and zero dynamics inside that leg. Patients have been practiced 15 minutes before shooting the videos, and they're able to change speeds from 0.3 meters per second to 1.1 meters per second. He's got an active ankle and active knee on that. And they don't want to give it back. They've been walking very, very comfortably. So go through it again really quick. It's natural walking. And so I think this is really the beauty of writing things up abstractly. So earlier this morning, one of you was saying, well, I don't have any cool examples. No, but you've got cool math. Others will find the examples maybe, okay? You don't always have to do everything.
I'm Aaron Ames. We're at the DARPA Robotics Challenge Finals,
that's
and we're
Aaron
looking
Ames.
at the humanoid robot Durus. So it's important to differentiate this robotic walking from a lot of the robotic walking seen throughout the competition. So everyone will notice the robots tend to hunch down and walk in a very slow and controlled fashion. So it's very non-human-like to walk like this, and that's not what we want.
At the DARPA Robotics Challenge.
Where we go and do what we do, right? So the difference here is we're no longer using these sort of pressure notions that these other algorithms build around. That's part of it for us. But really, this utilizes the whole dynamics of the robot and utilizes in a way that's formal and complete. So we can really leverage the...
So what Aaron is saying is that he's got hybrid zero dynamics going here. He's done all the optimization. But he didn't tell you, this robot was delivered to his lab 3 weeks before the competition. I would have crumbled, okay? These guys know I can take a lot of stress, but there comes a certain point. That's where all this gray hair is from. It's not from the students, from the robots screwing up, okay? I don't have kids, okay? But it's young, courageous guys like Aaron that mean he got that robot walking in 3 weeks, and he showed up in California, and it walked 7 hours a day on a single battery charge, okay? So that's when you get your math right, and I'll stop there. Thank you.
Thank you. We'll have some time for questions.
How about four-legged?
The expert on four-legged is Haewon Park. You hired him.
Anything that can be, any lessons learned from here to have a course, for example?
Yes, so former postdoc of mine, Kava Akbari Hamed at San Diego State, so he is taking the virtual constraint stuff, and he's got a four-legged robot with, is it 12 degrees of freedom, Haewon? 16, something like that. Yeah, so the fundamental thing here is synchronizing leg motion, right? So that part goes through. With 4 legs, you definitely have more than 2 legs in contact with the ground. 1 leg in contact, we have 2 or 3, or depending on the gait. So then your hybrid models become a little bit more complicated, because I was not doing single support, a non-trivial double support, then a transition. So Kava is going to have probably 6 bubbles in his hybrid model. His optimization problems are going to be a little bit more challenging. But yeah, I think he can get his robot to walk quite well with that. Please.
So one thing that I noticed was that one of the videos had robots slipping on something. How would you comment on reaction to that?
Robots slipping, yeah, so that's so what's typically happening there is, because we're not putting a sneaker on the end of our leg, and so when it hits, it'll vibrate a little bit. Yeah, and then if we're applying ground reaction forces fairly quick, then we are going to slip. So, the one solution is the mechanical one, where you put a little bit of a shock absorbing at the end of the leg, etc. But what we try to do is observe those and then go back to the optimization problem and then try to reduce leg impact velocities and things like that. So that's what we're trying to do, is take the observations and then bake them back into the design and have it automatically take care of that instead of putting the Band-Aids. But in all honesty, if I were turning this robot loose in the wild, I'd give it good shoes, okay? I still wouldn't power the ankles probably. I really like the passive ankles, to be honest with you. But I would make good things and reduce the amount of mechanical vibration. Because everybody who's worked on hardware knows that there's certain things that the control can take care of, but there's some things you should just fix in the hardware itself. And so things like backlash, just get rid of it, okay? And that's sort of like a backlash problem, I think.
Any more questions?
Oh, hey, Seth.
So there are at least 3 kinds of things that you can design here. One is the mechanical thing, one is the system of virtual constraints that you're going to use, and one is running around and not falling down, even though you toss stuff in front of it.
Yeah.
Do you know where the robustness is among those three?
Well, the guy who built the robot, Jonathan, says it's all in the hardware, okay? The student who designed the virtual constraints says it's all in the virtual constraints, and none of us think it's really exactly how we decided to impose those things going to zero, because we think we're using just kind of good solid, but nothing special there. So it's probably one of those two. But I don't know exactly how to sort those out. I mean, when the robot was walking across those planks in 3D with this broken harmonic drive, Brent had done the following in his gait optimization. He designed a periodic orbit, and then he included in his optimization the price of the robot taking a step up and a step down, so the cost, okay? And then he looked at how quickly he was able to converge from that perturbation back to something close to the periodic orbit, okay? And if at the end of the step there was a large difference between where the robot was versus where it would have been on the periodic orbit, he penalized that a lot, and then didn't penalize much early in the gait because you got a perturbation, you got to do something to respond to it. So he had deliberately done what he calls robust virtual constraint optimization. So for him, he really firmly believes it came from what he had built into those. And when he was walking up and down on the planarized version, the robot was told the world was flat, but that was not very flat, okay? There he had designed the constraints so that the robot could literally handle plus minus 8 centimeters ground height change per step. That's huge, okay? Now, when we do that in 3D, what we find is that when you have those types of perturbations, then the coupling with the lateral and sagittal plane dynamics becomes really important. Because if you slow down the robot in the sagittal plane, it now has a long time to oscillate on this foot, okay? And so if you get those oscillations out of synchronization, bad things happen. Where if you're on a boom, there's only one notion of oscillation, and it going faster and slower has no effect on the other because of the mechanical constraint. So we don't think in 3D he'll be able to handle that for a long time, this plus minus 8. We should be able to do plus minus 4 with no problem. And the slopes that go from the Double E building up to Beale Avenue, if you've been there and stuff, I think we can handle that very easy with the robot thinking it's on flat ground, that type of stuff. And so.
Okay, let's thank Professor Grizzle. So we'll have a 10-minute break, and after that it will be our second student session on robotics and control.